Okay. All right, welcome back from the break. Before we jump into Q&A, there was one thing I did want to note that's a subtlety. If you have a rectangle or any other surface and you have a length or a parameter of its geometry that's defined by a symbol, then you can't use the grips to extend it. So if I had said that this rectangle was x max long, I'm not allowed to use the grips to extend it. It will always remain x max. So if you are using symbols to define your geometry, that might limit your use of grips, as we demonstrated earlier with the CubeSat model to be able to extend surfaces. So otherwise, are there some questions? I'd love to hear them. So usually I choose the outside because that's the outer surface for radiation. Most of the things that we're doing are thin shells. So if it's a ½ an inch difference and it's 60 inches wide, that ½ an inch doesn't really make much of a difference in it. So if it's a thicker surface, it might not be reasonable to represent it with the 2D planar surface. If it's very thick, I might have to go with a solid at that point. I could choose either an FD solid or I could use solid elements for it. So you do have to make the decision as to whether you can abstract the thickness of your geometry to a two-dimensional surface and use the thickness properties, or whether you actually have to model it as three-dimensional with the gradient through the thickness. Does that answer the question? Okay. Do you wish to ask your question for the group on the MLI? Okay. So it is true that when you get to finite elements, a conductor between two nodes no longer represents the heat flow. That said, I'm not very, sorry, let me take the mask off. I'm usually not too interested in the energy into a single node, but a group of nodes. And there, it still holds. And when we get to the Cinda portion a little later on, you'll see the difference between a centroid approach, a finite difference approach, and finite element approach, where the finite element has negative conductances, which makes no sense to people who are thinking of conductivity as a Ka over L one-dimensional. But from a control volume point of view, the energy balance still holds. So it still balances the energy coming in, energy going out there. So you can still look at heat flows across interfaces using finite elements. It just can't be at a nodal level for it to make sense. But do I really care about the heat flow between here and here, or do I care more about the heat flow between this quadrant and that quadrant? So from my point of view, I trust that it's correct. It's one of the things I have left to do in my career is to truly understand how they get the conductance matrix in there. But I usually am looking at this group of elements to that group of elements, or this group of nodes to that group of nodes. And so I'm not interested in, per se, one conductance path. I'm interested in the conglomerate of many of them. Does that answer the question? Okay. So if I want to get the area of the MLI, I would have to manually click points and say, what's the area of this? But if I take the volume of the MLI, which will be based on the geometric area that it has, times that thickness parameter, I can take the volume multiplied by a density to get a mass. I can't take the area multiplied by density to get a mass because I'm off in the units. So it doesn't have to be 1 meter, but whatever you have selected for the density for your material property for MLI needs to use the same thickness that you're applying there. So when I think of MLI mass, I think of it in terms of it's 0.6 kilograms per meter squared. That's my rule of thumb. So if I say 0.6 kilograms per meter cubed, that's the meter squared times the 1 meter thickness, and it's just something I recognize when I do it. I could have said, okay, let's do 0.6 kilograms per meter cubed, but let me scale it for a 1 centimeter thick, and then put the 1 centimeter thickness in. So as long as you're consistent, you could use that trick to get the mass. It doesn't have to be a meter, it just has to be consistent. Is that clear?
Yeah, thank you so much.
You're welcome. We will get to that when we talk about meshers. So there are many meshers on the market. There's Space Claim, which has it. There's FEMAP. There's the mesh controllers in Thermal Desktop. But it requires that you define your CAD to be able to be meshed appropriately. And we'll show how, if you don't do that, you can suddenly go from this to 50,000 elements, which just isn't really needed for something that can be done with a few hundred elements. So there are meshers to be able to do that, but sometimes they don't produce the best models for thermal. And when you have radiation, 50,000 surfaces that all see each other goes as n squared, and suddenly your radiation coupling count goes very high, and your model runtime goes very long. So it may be quicker for you to push a button and get it, but it will take you longer to get results potentially than to do it manually. So I like to control how dense the mesh is myself rather than let the software do it. But there are times where an auto mesher is an appropriate path. Does that answer your question? So changing it on multiple elements?
Yes.
You just select multiple elements. So if I were to select all of these, here, let's just do it. Let's say that I wanted just the top ring to only have MLI on the outside and not on the inside. So I can select all of these elements and then edit them as a group.
Oh.
And so now here it's asking me, it's saying, hey, I found different types of things. I found some thin shell elements and I found some nodes. Which of those do you want me to operate on? In this case, I'm going to operate on the 16 elements. And so if I say OK, I could say for insulation, I want it, let's take it off and hit OK. And so now when I visualize insulation, these have no insulation on them.
Thank you very much.
So, yes. So you can edit multiple surfaces at a time, and it will apply the changes to anything that's different. Clear? that is mostly engineering judgment. As I see it, something that is thin and a low conductivity material, titanium, a composite, I need more nodes for because I have a larger gradient through it. Something that's very thick and aluminum, high conductivity, there's not enough of a difference between the calculation points to say I need 20 nodes here. That, you know, over those 20 nodes, if it increases a quarter of a degree, why do I need all that granularity between it? So it really comes down to engineering judgment. Thick, high conductivity surfaces, you need less nodalization. Thin, low conductivity, you want more nodalization. Yes. You can if you have the time. Very often it's you know, okay, I could do it, but it's difficult to do something like this, to do a mesh conversion study, because how do I make that finer mesh? So there is a refine elements option, and I'll just show you what that does real quick, where it will take this quad and turn it into 4 elements. So I could, if I was really concerned about it, say, let's refine all of these elements. And now you can see my mesh is much greater. But it's not going to give me options other than turn a quad into 4, turn a triangle into 4 triangles. That's it. It doesn't, it's not selective. And if I were to try to only do a portion of it, well, now I wind up with 3 nodes along an edge for one element and 2 nodes along an edge for the other element, and I've broken a link in there. So if I were really concerned about the mesh density and its accuracy, I could do this. But you can see how many more nodes I have now. The computation time would go up. Does that address the question? Once you get to a point where you actually have hardware that's built and you put it into thermal vac, you ideally like to have thermal balance cases. We typically go with 3, a hot balance, a cold balance, and a survival balance, at which point we have a criteria that says it has to be stable enough for the thermal engineer to be happy, such that my mass times capacitance times specific heat is 0. So now I will take that data, get as many measured values as I can from thermocouple sensors, flight telemetry, and power inputs, and then I will adjust the model with the things where I feel there's uncertainty, E-star values, interface conductances, and so on and so forth, to try to tune the model to best match the data that I have from test. Once that model is correlated, as we call it, then the flight predictions are made from that and compared against their limits. But that comes much, much later in the program because hardware is expensive. It costs a lot to build it. So, you know, you go through many, many, many design iterations analytically of simulations in a virtual model before you have actual data to compare to. But it does certainly happen. You want to correlate the model to the test data under known and controlled conditions.
Thank you very much.
Yeah. Now, that said, for the Northrop case, JWST was so difficult to test, so large, cryogenic, there's so many new things on it that to reduce the risk, they had 2 teams of people modeling the design that tended to try to work as independently as possible. And if you both came to the same answer, you felt a little more confident that you both got it right. You might have both gotten it wrong, but you felt confident you both got it right. And if you saw discrepancies, you then said, okay, well, who's right, who's wrong? You looked a little bit closer at that area of the design to understand why one person saw X and the other person saw Y. Okay, other questions? Not so much for this. I might later, and we'll show that, if I look down from the top of this, it's not a perfect cylinder anymore. Yeah. So you have to decide whether you can live with that or not. You can see some areas here, where, okay, there's some skew to it, but does it matter? That's a judgment for the engineer. In this case, when we went through and we made the disc a little bit smaller to make sure it didn't cut through, it turns out we made it too small in areas and you got some solar energy peeking through. And if you go through all the slides, you'll see that happens in here. So again, it's a judgment call, but if you wanted to more closely match the exact geometry, you need more surfaces, more elements, more nodes to do it. So it again comes back to judgment. Is this good enough? And we have a phrase that says, perfect is the enemy of good enough. So if I have something that needs to be done quickly, probably not too worried about the fact that it might be off by a half a centimeter or half a meter. Well, half a meter, I'd be worried. So, it does come down to judgment. But yes, that is a recognition that you have to make, that it's not going to be perfect. Yes, you would. This is a starting point. Does the design look like it's feasible? Are there anything? These studies are basically where, at least this one, you come in with a set of requirements, and they would like a design within a week, and then they want the costs another week after that. So this is really early level, before phase A. This is, do you see things that would be a problem with going forward with this design? By the time you would get to flight, you'd have a much more detailed model, much more granularity, much more accurate, but probably within 5 or 10% quality-wise of what this is in terms of the predictions. You want something that's close enough to tell you that, yes, this design is feasible. I haven't necessarily found a case where I would choose centroids over edge nodes. Centroids are how it used to be done when I first started. There weren't really edge nodes. I find edge nodes to be a good halfway point between finite elements and centroid nodes. There are some codes, Esotan tends to go with the centroid node approach, but they have an automatic conductor generation that goes from the centroid location to the interface to the next one and makes that connection. So centroids are fine to use. It just might mean a little more work for you to connect one centroid to another that are on different surfaces. The edge nodes really are a finite difference 1D approach that's very similar to centroid. It just changes the lengths and the cross-sectional areas through which the heat flows to the locations where the nodes are along the edges rather than at the centroid. So the other challenge with centroids is, again, at interfaces between surfaces, you have to manually find a way to make the connection. So that's where I think the edge nodes have a strength, is when I can merge nodes between two contiguous parts, or the same part, just different areas of the geometry of it. It just becomes easier to not have to figure out how to connect node 1 to node 2, because the software is programmed to do it. You're welcome. All right, anything else, or shall we continue with the model building? Okay, so the RAT-Ks are actually done, and I'm starting to talk now beyond where I actually have full experience because I didn't write the code, but when a ray hits this surface, say right here, from my understanding, what Kolmorn Ring does is they have these, what they call Galerkin shape functions, which are used somehow in the definition of finite elements that would apply a higher weighting factor to this node and this node that are closer to this location than that node and that node. And so when the ray comes in and it hits here, some of the energy goes here, some goes here, some goes here, some goes here, based on those shape functions in order to do it. So it's not all to one section. I believe that TSS, which was a precursor to that, used a subdivision, so it would divide this, and if it hit into this corner, all of the energy went to that node. The area for this is just geometric if you look at the whole element, but if you're trying to see the sub-area associated with each of these, again, I think those shape functions distribute it differently. You know, more of it goes as you're closer to the node. So it's not all of it goes into one node. It is spread out based on the distance between the location where the ray hit and the rest of the nodes. It's based on geometry. And that's probably based on the raw geometry. So if I applied heat to this element, it would distribute it equally based on the area here. So if I distribute to the node, then it goes directly to the node. So, you know, so you can't say distribute it to this part of the element. It's either the node or the whole element, and if it's the whole element, then it uniformly distributes it. Okay, good?